Okay, good morning. Yes, my name is MARKO. I'm a research scientist in Kemira R&D, and I have a couple of examples, industrial case examples. The first one is kind of fully commercial and full-scale technology, and the another example is kind of more like in development stage. Okay, but first I would like to start with a couple of kind of sustainability aspects. So Kemira's vision is to become the leading provider of sustainable chemistries for water-intensive industries. Currently we have more than 100 million sustainable product sales, and we are targeting 500 million by 2030. And today, 21% of the total carbon in our carbon-containing products is renewable carbon. And that we are targeting to increase to 40% by 2030. Okay, with our chemistries, we create better every day for all of us. And we are aiming to make it better every day. So this is what we mean with chemistry with purpose. So we share United Nations Sustainable Development goals and have picked four topics there that are match best to us. So people aspect. So how we have kind of all these people thought in our supply chain, and then water. Water, of course, it's a core of our business, so we help our customers to reduce water consumption, to manage water quality and so on. Then circularity, we use recycled raw materials, and we help our customers to create circular solutions for their customers. And then climate, we of course improve our own carbon footprint, but we also develop solutions to help our customers to reduce their carbon footprint. And the safety is the foundation of all of this work. So safety means also, safe business means also sustainable business. So by safety we mean safe products, safe processes, people safety, and so on. Okay, so let's go then to the first case example. So polyacrylamides. So Kemira is actually leading global producer of polyacrylamides, and these are water-soluble polyelectrolytes that are being used as, for example, as a retention aids in paper and board manufacturing, flocculants in municipal and industrial water treatment, and then as viscosity modifiers in variety of applications. And acrylamide monomer is the main building block of these polyacrylamides. There are also co-monomers, but acrylamide is the main one. Okay, so if we go in detail to acrylamide monomer synthesis, so it is actually enzymatic synthesis, and this is actually one of the big success stories in chemical industry about enzymatic synthesis. So today Kemira is making all acrylamide based on enzymatic hydration of acrylamide. So it's made at ambient conditions, and it's exothermic reaction. It looks simple, but it's not that simple. So the kinetics is quite interesting, but the benefits are really great compared to this previous technology, state-of-the-art technology, chemically catalyzed copper technology. So next slide I have a comparison of these two technologies, and I try to shortly explain why it's so good. So basically this enzymatic synthesis is done at ambient conditions compared to copper catalyzed at high temperature, high pressure. This means, of course, better process safety. Actually, it's excellent, thinking that now we are making a monomer. So monomer is always at risk to start polymerizing. That creates lots of heat and risk of runaway. So making this synthesis at ambient conditions is actually makes it very, very safe. And also minor emissions. Then yield is good compared to this copper catalyzed process. So in copper catalyzed process at high temperature we always lose some feedstock as polymer and other side reactions. We generate very little waste while in this copper catalyzed process we have lots of this polymeric waste and also hazardous waste because it contains this copper as inhibitor. Energy consumption is low compared to copper process where we need distillation to separate unreacted acrylonitrile and recycle it back. Process is very simple. Basically, it's just one process step compared to this copper catalyzed process, and that means easy process operation and also very low investment costs. So this is example about this process efficiency improvement. But that's not all. We also are kind of targeting to make our feedstock for this process more sustainable. And basically on the left-hand side you can see this kind of circular economy thinking related to our pulp and paper customers. So they are making as their in their processes biomass side streams that we can then basically or not us, but together with our partners, we can convert, that can be converted to biopropylene and further to bioacrylonitrile that can then be used as feedstock to raw material to our processes. Or on the right hand side, our water treatment customers, they are generating kind of sludge as waste that can be digested to biogas. And from biogas, it is possible to make, for example, ammonia or methanol that is being used then as feedstock to make our monomers. And then we can make our products, bioacrylamides, and then we can sell those to our customers. So very nice circular economy thinking. And actually, Kemira is the first producer selling this kind of certified biomass balanced polyacrylamide. So we launched this product end of last year. Okay, and what is the benefit? So actually it's identical product, quality and performance, no need for lab or pilot trials, it's really drop-in product. Customers can use their existing process, we can use our existing manufacturing assets without changes, and we save fossil resources and increase the share of renewable raw materials. So on the right hand side you can see a kind of estimation we made based on all these ISO standards and life cycle assessment methods. So we estimate that depending on the degree of cationization, this carbon footprint or emission reduction potential is from 50 to up to 100%. Okay, another case. So we are working together with our partner IFF to kind of commercialize this kind of new to the world biopolymers concept and platform based on enzymatic polymerization. So basically this is polymerization of glucose coming from sugar crop, sugarcane, sugar beet, and this is done enzymatically, meaning that it's resource and cost efficient, again ambient conditions. Our partner IFF has good technology readiness to scale this up. There is good freedom to operate, very strong IP position, and the most interesting thing here is that these man-made polysaccharide properties are tunable. So there can be fibrates, there can be microcrystallized polysaccharides, there can be linear, there can be branched, and on top of that, of course, these polysaccharides can be derivatized to get more functionality to these products. So Kemira's contribution here is to tune these properties and develop high-performance applications to paper and board to improve their manufacturing efficiency, improve product strength and lightweighting. Also we are developing barrier properties to packaging based on this technology, and to sludge dewatering in municipal water treatment. Okay, and this is my last slide. So this is also a sustainable chemical platform. So it's 100% bio-based content, reduces emissions and depletion of fossil resources. It's based on sucrose feedstock from high-yield crops, and of course this is quite important from sustainability point of view. So we are able to minimize then the land use impacts of this bio-based feedstock. These products are fully recyclable and biodegradable, and this enables then multiple end-of-life options and avoids microplastic pollutions. On the right-hand side, I have one example of emission avoidance to recycled cellulose furnace, drainage and dewatering application by these products, and here we are comparing to commercial polyvinylamine product that our customers are using. So, and the values are, this is really delta, so the benefit, so kilos of CO2 equivalent per metric ton of dry pulp avoided. And this is at different stages of the life cycle. So the first is chemicals manufacturing, some reduction, but then the major benefit in handprint. So actually because this enables drier, improved kind of dewatering compared to this benchmark product, so we get really nice handprint benefit from this new product. And at the end of life, because it contains biogenic carbon, so it, if we assume incineration as end of life option, so then we are emitting biogenic carbon, and that gives the benefit compared to this fossil product. Thank you, that was my talk, so any questions?